By the end of the 19th century, physics stood with an air of triumph that is rare in the history of human thought. For over 200 years, the motion of planets, the fall of apples, the swing of pendulums, and the flow of rivers had all bowed obediently to the laws first written by Isaac Newton. Matter moved according to precise mathematical rules, and those rules worked with astonishing accuracy. Later, James Clerk Maxwell unified electricity, magnetism, and light into a single elegant theory of electromagnetic waves. Heat was understood in terms of the motion of atoms, and thermodynamics laid down powerful principles governing energy and entropy. The universe appeared orderly, predictable, and ultimately understandable, like a grand clock whose gears were finally mapped in detail. This confidence was not arrogance without reason. The equations of classical mechanics could predict the return of a comet decades in advance. Engineers used them to design bridges, engines, and machines that transformed society. Maxwell's equations not only explained light, but also predicted radio waves, which were later detected, confirming theory with experiment. The kinetic theory of gases linked microscopic motion with macroscopic properties such as pressure and temperature. Everywhere scientists looked, the classical framework seemed to work. Many leading physicists believed that only minor refinements remained, small corrections to known laws. Some even suggested that the great era of discovery in physics was nearly over. Yet beneath this confidence, cracks had already begun to form. These cracks were not obvious failures like a machine breaking down. Instead, they were subtle mismatches between theory and experiment, small puzzles that resisted explanation. At first, they seemed like technical issues, the kind that would be resolved with more careful measurements or better mathematical treatment. But as the years passed, these puzzles multiplied, and their persistence hinted at something deeper. Nature was quietly signaling that the classical picture, however powerful, was incomplete. One source of tension came from the behavior of light. Classical physics treated light as a wave, an oscillation of electric and magnetic fields traveling through space. This wave picture explained reflection, refraction, interference, and diffraction beautifully. But certain experiments began to show that light did not always behave like a smooth, continuous wave. The interaction of light with matter revealed strange patterns that did not fit comfortably within the classical framework. Still, these issues remained in the background, not yet recognized as signs of a coming revolution. Another growing difficulty involved the structure of matter itself. Atoms were widely accepted as the building blocks of matter, but their internal workings were mysterious. According to classical electrodynamics, an electron moving in a circular orbit around a nucleus should continuously emit radiation, losing energy and spiraling inward. In a short time, the atom should collapse, yet atoms are stable. Matter does not spontaneously implode. The classical laws, when applied at atomic scales, seemed to predict a universe that could not exist. This contradiction was deeply troubling, though it was not yet fully understood. Heat radiation provided the most dramatic and undeniable challenge. When an object is heated, it emits electromagnetic radiation. A piece of iron in a furnace glows red, then orange, then white as its temperature rises. Physicists sought to describe this radiation in terms of known laws of electromagnetism and thermodynamics. They imagined the radiation inside a cavity, bouncing off the walls and reaching equilibrium with the matter. Using classical ideas, they derived formulas for how much energy should be emitted at different frequencies. At low frequencies, these formulas worked reasonably well, but as the frequency increased toward the ultraviolet, the predictions went wildly wrong. The equations indicated that the energy emitted should grow without bound, becoming infinite. This absurd result implied that even a moderately warm object would radiate an infinite amount of energy, which clearly contradicts reality. This failure was not a small discrepancy. It was a catastrophic breakdown of theory, later called the ultraviolet catastrophe. It exposed a fundamental flaw in the classical assumption that energy could vary continuously. The problem was not due to sloppy mathematics or poor measurements. Experiments were becoming increasingly precise, and they consistently disagreed with classical predictions. The failure suggested that the very foundations of the theory, the assumptions about how energy is distributed among electromagnetic waves, might be wrong. Yet abandoning classical ideas was unthinkable to many. These ideas had worked so well for so long that questioning them felt like undermining the entire structure of science. The crisis deepened with the study of specific heats of solids. According to classical theory, atoms in a solid vibrate and share energy equally among available modes of motion. This led to a simple prediction: the specific heat of a solid should be constant, independent of temperature. But experiments showed that at low temperatures, the specific heat drops dramatically, approaching zero. Classical theory could not account for this behavior. Once again, nature refused to follow expectations based on continuity and smooth energy exchange. The motion of electrons in metals presented another puzzle. Classical models treated electrons like tiny charged particles moving freely, colliding with atoms much like molecules in a gas. These models predicted certain electrical and thermal properties. While they captured some features, they failed to explain others, such as the detailed temperature dependence of conductivity. The more carefully scientists measured, the clearer it became that something essential was missing. These problems shared a common theme. Classical physics assumed that physical quantities such as energy could change in arbitrarily small, continuous amounts. Whether it was a vibrating atom, an electromagnetic wave, or a moving electron, energy flowed smoothly, like water being poured. But experiments suggested that, at microscopic scales, this smoothness might be an illusion. The distribution of energy did not behave as expected when systems became very small or very cold. The classical picture, built on continuity, was colliding with a world that seemed to have a hidden structure. Despite these warning signs, the crisis was not immediately recognized as a crisis. Scientists often work by adjusting existing theories, adding corrections or new mechanisms while keeping the core framework intact. Many believed that with enough ingenuity, the puzzles would be resolved within classical physics. The authority of Newton and Maxwell was immense, and abandoning their world, you required extraordinary evidence. What made the situation especially difficult was that classical physics worked perfectly in everyday conditions. Planets still followed predictable orbits. Projectiles still obeyed familiar trajectories. Machines still ran according to Newton's laws. The failures appeared only under special circumstances, at very high frequencies, very low temperatures, or very small scales. It was as if the familiar laws were an approximation, valid in the macroscopic world, but breaking down in a hidden microscopic realm. This realization, though not yet fully formed, marked the beginning of a profound shift. Instead of assuming that the same rules applied at all scales, scientists began to suspect that nature might operate differently in the atomic domain. The crisis in classical physics was not the collapse of everything that had been built. Rather, it was the discovery of limits, boundaries beyond which old concepts lost their meaning. The emotional atmosphere among physicists was complex. There was excitement at the new experimental discoveries, but also discomfort and confusion. Some clung to classical ideas, hoping for a clever fix. Others sensed that a deeper change was coming, but could not yet see its form. The stage was set for a breakthrough that would require not just new equations, but a new way of thinking about energy, matter, and light. In this tense environment, the problem of heat radiation stood out as particularly urgent. It was precise, measurable, and undeniably inconsistent with theory. Solving it meant confronting the foundations directly. It was here, in the attempt to understand how hot objects glow, that the first decisive step toward quantum theory would be taken. The crisis in classical physics was not a dramatic explosion, but a slow tightening of contradictions, drawing science toward a turning point where continuity would give way to discreteness, and certainty to a new, stranger vision of reality. Long before the language of quanta entered science, the simple glow of heated objects had already become a silent messenger of deep physical truths. When a piece of metal is placed into a fire, it first darkens, then begins to emit a dull red light, which grows brighter and shifts toward orange, yellow, and eventually white as the temperature increases. This change in color is so familiar that it feels almost trivial, yet hidden inside it is one of the most profound mysteries physics ever faced. The light emitted by a hot object does not depend strongly on its shape or chemical composition. Instead, it follows universal rules linked only to temperature. Understanding those rules became a central challenge at the end of the 19th century. Scientists imagined an idealized object to study this radiation, a blackbody. This was not literally black in color, but rather an object that absorbs all incoming radiation perfectly and emits radiation in a way determined solely by its temperature. A cavity with a small hole in its wall served as a practical approximation. Light entering the hole would bounce around inside, being absorbed and re-emitted many times, eventually reaching equilibrium. The radiation escaping through the hole represented the pure thermal radiation of the cavity, independent of material details. This setup allowed physicists to focus on universal behavior rather than the complexity of real materials. Careful experiments revealed that the intensity of radiation from a blackbody depends strongly on frequency. At a given temperature, there is a particular frequency at which emission is strongest. As temperature rises, this peak shifts toward higher frequencies, meaning shorter wavelengths. This is why hotter objects appear bluer, while cooler ones glow red. The relationship between temperature and peak wavelength became known through Wien's displacement law, an early success in describing blackbody radiation. Yet knowing the position of the peak was only part of the story. The full distribution of energy across all frequencies remained to be explained. Physicists turned to classical electromagnetism and thermodynamics to derive the spectrum. Inside the cavity, electromagnetic waves could form standing patterns, much like sound waves in an organ pipe. Each pattern, or mode, could store energy. Classical statistical mechanics assumed that energy would be shared equally among all available modes, an idea known as the equipartition theorem. This seemed reasonable, as it worked well for gases and many other systems. When applied to radiation, however, it led to a startling prediction. The number of possible wave modes increases rapidly with frequency. There are far more ways to form high-frequency standing waves than low-frequency ones. If each mode receives the same average energy, then the total energy at high frequencies should become enormous. In fact, the classical formula, later called the Rayleigh-Jeans law, predicted that the energy density grows without limit as frequency increases. Mathematically, it diverged toward infinity. Physically, this implied that a hot object should emit infinite energy, mostly in the ultraviolet range. This result was clearly absurd. No furnace explodes with infinite radiation. Measurements showed that the intensity of radiation actually drops off at high frequencies. The spectrum rises from low frequencies, reaches a peak, and then falls. The classical prediction matched experiments only at the low frequency end. Beyond that, theory and reality parted ways dramatically. The term ultraviolet catastrophe captured both the mathematical divergence and the conceptual crisis. It was a catastrophe not of nature, but of theory. The problem was especially troubling because the reasoning behind the classical result seemed solid. Maxwell's equations described electromagnetic waves with great success. Statistical mechanics had explained the behavior of gases and heat. Combining them to describe radiation felt like a natural extension. Yet nature refused to comply. The failure suggested that at least one of the underlying assumptions must break down under these conditions. One suspect was the equipartition theorem. This principle relied on the idea that energy could vary continuously and be divided among modes in arbitrarily small amounts. But what if, at microscopic scales, energy exchange was not continuous? This thought was radical. Continuity was deeply woven into classical physics. Motion, energy, and fields all changed smoothly in time and space. To question this smoothness was to question the very fabric of the classical world. Experimental work grew increasingly precise. Researchers measured radiation spectra at different temperatures, carefully mapping the distribution of energy. The curves were smooth, reproducible, and universal. They did not depend on the material of the cavity walls, confirming the idea of blackbody radiation as a fundamental phenomenon. Any successful theory had to reproduce these curves exactly, not just approximately. Attempts were made to patch the classical theory. Some scientists proposed modifications to the way matter interacted with radiation. Others adjusted assumptions about boundary conditions or the nature of oscillators in the cavity walls. None of these efforts resolved the high-frequency divergence while still agreeing with low-frequency behavior. The problem resisted incremental fixes. At the heart of the mystery was the interaction between radiation and matter. The walls of the cavity contain charged particles, which can oscillate and emit or absorb electromagnetic waves. Classical theory treated these oscillators as systems that could take on any energy value, increasing or decreasing smoothly. If many such oscillators were present, they should exchange energy with the radiation field until equilibrium was reached. But the observed spectrum implied that high-frequency oscillators somehow failed to acquire the energy predicted by equipartition. This hinted that something was limiting the amount of energy available at high frequencies. But what mechanism could impose such a limit? No classical process seemed capable of doing so. The equations of motion did not include any natural cutoff. The divergence arose inevitably from the mathematical structure of the theory. The Blackbody problem thus became a focal point where theory, experiment, and philosophy collided. It forced scientists to confront the possibility that their most trusted principles might not be universally valid. The smooth, continuous exchange of energy, so central to classical thinking, might be only an approximation. Beneath it, a different set of rules could be operating, invisible at everyday scales but decisive in the microscopic realm. The glow of heated objects once a mundane observation, turned into a doorway to new physics. It was not an exotic phenomenon in distant stars or rare materials. It was present in every flame, every heated wire, every star in the night sky. Its universality made the puzzle even more compelling. Solving it meant uncovering a principle woven into the structure of nature itself. As the 19th century closed, the mystery of Blackbody radiation stood unresolved, a challenge waiting for a bold idea. The failure of classical theory here was not just a technical glitch. It was a sign that the path forward required a departure from deeply held assumptions. The stage was set for a conceptual leap, one that would transform the understanding of energy and mark the beginning of a new era in physics. At the turn of the 20th century, the problem of heat radiation weighed heavily on the minds of physicists. Experiments were precise, the data curves smooth and reliable, yet theory stumbled. The distribution of energy emitted by hot objects simply would not obey the expectations of classical physics. The equations derived from well-established principles rose toward infinity in regions where measurements clearly showed a decline. Nature's behavior was calm and finite, while theory predicted chaos. It was in this uneasy space between confidence and contradiction that a quiet, methodical thinker named Max Planck found himself searching for an answer. Planck did not approach the problem as a revolutionary eager to overthrow old ideas. He was deeply trained in thermodynamics and believed strongly in the power of fundamental laws. His goal was modest in appearance: to find a mathematical formula that matched the observed radiation spectrum. He studied the experimental curves carefully, especially the way energy varied with frequency at different temperatures. He knew that any correct description had to smoothly connect the low-frequency region where classical results worked with the high-frequency region where they failed. Inside the walls of a heated cavity, charged particles oscillate and interact with electromagnetic fields. Planck imagined these oscillators as tiny systems capable of emitting and absorbing radiation. The key question was how energy was shared between matter and radiation. Classical theory assumed that oscillators could take on any energy value, increasing or decreasing continuously. This assumption, when combined with statistical mechanics, led directly to the ultraviolet catastrophe. Planck realized that keeping this assumption untouched would never solve the problem. In October 1900, he tried a new approach. Instead of deriving the spectrum strictly from first principles, he constructed a formula that fit the data and then worked backward to interpret its meaning. This was an unusual move for him, almost a compromise between theory and experiment. The formula he found matched the entire observed curve beautifully, but its deeper significance was not yet clear. To justify it, he turned to the concept of entropy and the statistical behavior of oscillators. Here, Planck made the step that would change physics forever. In calculating how energy could be distributed among oscillators, he did not treat energy as continuously divisible. Instead, he assumed that the energy of each oscillator could only take on certain discrete values, proportional to its frequency. The energy, he proposed, came in tiny packets. The size of each packet was given by a new constant multiplied by the frequency. This constant, later known as Planck's constant, was extremely small, but its implications were enormous. This assumption was not introduced with dramatic flair. Planck later described it as an act of desperation, a formal trick to make the mathematics work. Yet it was a break from centuries of continuous thinking. If energy exchange occurred only in fixed amounts, then high-frequency oscillators would require larger packets of energy to be excited. At ordinary temperatures, there would not be enough energy available to populate these high-frequency modes significantly. This naturally suppressed the radiation intensity in the ultraviolet region, exactly as experiments showed. The beauty of the idea lay in how simply it resolved the catastrophe. The divergence predicted by classical theory disappeared. The spectrum now rose at low frequencies, reached a peak, and declined smoothly at high frequencies. The formula agreed with measurements across the entire range. A single new assumption about the discreteness of energy restored harmony between theory and observation. What made this step so bold was that it contradicted the deeply held belief in continuity. Classical physics viewed energy like a fluid that could flow in infinitely small amounts. Planck's model treated energy more like currency, exchanged in indivisible coins. The oscillators could not possess arbitrary energies, but only multiples of a basic unit. This was a conceptual leap into unfamiliar territory. Planck did not immediately interpret this quantization as a property of radiation itself. He applied it to the oscillators in the walls, not to the electromagnetic field in empty space. Even so, the introduction of discrete energy elements planted the seed of quantum theory. The constant he introduced, symbolized by h, set a fundamental scale. It linked energy and frequency in a way that had no counterpart in classical physics. The smallness of h explained why classical physics worked so well in everyday life. The energy packets are so tiny compared to macroscopic energies that the discreteness is effectively invisible. Systems with large energies involve enormous numbers of quanta, making energy appear continuous. But at atomic scales, where energies are comparable to a few quanta, the granularity becomes crucial. The hidden structure of nature begins to show. Planck presented his results in December 1900 to the German Physical Society. At the time, the deeper meaning was not widely appreciated. Many saw it as a clever mathematical device rather than a new physical principle. Planck himself was cautious, unsure whether the quantization reflected reality or merely a useful approximation. Yet the success of the formula was undeniable, and the constant h quickly became a fixed feature in calculations involving radiation. This moment marked the birth of a new way of thinking, though few recognized it immediately. A small adjustment introduced to solve a specific problem had opened a path beyond classical physics. The idea that energy exchange might be fundamentally discrete challenged the smooth landscape of earlier theories. It suggested that at the microscopic level, nature operates with steps rather than flows. In hindsight, Planck's assumption appears as the first crack in the classical world, that would widen into a full transformation. It provided a bridge between experiment and theory where none had existed. By daring to treat energy as coming in packets, he replaced infinity with finiteness, chaos with order. The ultraviolet catastrophe, once a symbol of failure, became the gateway to quantum reality. When Max Planck introduced his radiation formula at the dawn of the 20th century, one element of his work stood out as both mysterious and profound, a new constant of nature. This number, small beyond everyday imagination, linked the energy of radiation to its frequency. At first, it appeared as a proportionality factor, a mathematical necessity that made the equations fit experimental data. Yet over time, this constant became recognized as a fundamental feature of the universe, marking the scale at which the familiar rules of classical physics give way to a different order. In classical science, constants such as the speed of light or the gravitational constant already played central roles. They set limits and determined the strength of interactions. but Planck's constant did something more subtle. It did not merely scale a force or speed. It determined the size of the smallest possible exchange of energy between matter and radiation. In Planck's formulation, the energy of an oscillator could take only values that were whole, number multiples of this constant times the frequency. Energy was no longer a smooth continuum, but arranged in discrete steps, and the height of each step was governed by this new quantity. The value of the constant is extraordinarily small. In ordinary situations, energies are so large compared to this basic unit that the steps blur into what looks like a continuous ramp. A bouncing ball, a moving car, or even a vibrating guitar string involves energies made up of countless quanta. The granularity is hidden, much like individual grains of sand in a distant beach appear as a smooth surface. Only when systems shrink to atomic scales does the discreteness become visible and unavoidable. This constant, later symbolized by the letter H, quickly appeared in many new contexts. It became clear that it was not just a detail of thermal radiation, but a universal marker of quantum behavior. When scientists studied how atoms absorb and emit light, they found that electrons could occupy only certain energy levels. Transitions between these levels involved the emission or absorption of light with frequencies determined by the energy differences divided by h. Spectral lines, the sharp colors seen in atomic emissions, were direct evidence of quantized energy controlled by this constant. The appearance of h reshaped the understanding of motion as well. In classical mechanics, a particle can have any position and momentum simultaneously, limited only by measurement precision. But in the emerging quantum framework, Planck's constant set a fundamental limit. It entered into relations that bound how precisely certain pairs of physical quantities could be known. The microscopic world was no longer governed by exact trajectories, but by probabilities, with h defining the scale of this indeterminacy. Planck himself did not immediately grasp the full significance of the constant he had introduced. To him, it was initially a parameter emerging from statistical arguments. Yet, as other physicists explored its implications, they found it woven into the fabric of diverse phenomena. Albert Einstein used the relation between energy and frequency to argue that light itself comes in discrete packets, later called photons. Niels Bohr employed the constant to describe stable electron orbits in atoms, explaining why atoms do not collapse. Each success reinforced the idea that h was not an artificial construct, but a window into nature's underlying structure. What makes this constant remarkable is that it defines a boundary between two worlds. When physical actions are large compared to h, classical physics provides an excellent approximation. But when actions approach the scale of h, quantum effects dominate. This boundary is not about size alone, but about the scale of energy, time, and motion. It explains why quantum phenomena seem strange and unfamiliar. They operate in a regime far removed from human experience. The constant also carries deep philosophical implications. Classical physics suggested a universe that could, in principle, be known with unlimited precision. With h in the picture, nature imposes limits that are not due to experimental imperfections, but to the structure of reality itself. This shift from certainty to fundamental limitation altered not only equations, but also the world of science. As research progressed, Planck's constant appeared in the description of matter waves, chemical bonds, and the stability of solids. The behavior of electrons in metals, the colors of substances, and the mechanisms of chemical reactions all depend on quantized energy levels governed by h. Technologies that define modern life, from semiconductors to lasers, operate on principles where this constant plays a central role. What began as a term in a radiation formula became a cornerstone of modern technology. The universality of the constant suggests that discreteness is not an isolated feature, but a basic trait of the universe. It is as if nature has a smallest unit of action, a graininess underlying the smooth surfaces perceived in daily life. Planck's constant measures this graininess. It tells us how finely energy and motion can be divided before the classical picture dissolves. Over time, the constant's role expanded further through the development of quantum mechanics. In wave equations describing particles, h determines the wavelength associated with motion. It connects the particle, like and wave, like aspects of matter. Without it, the strange dual nature of quantum objects would have no scale. Its presence ensures that quantum waves have dimensions and effects consistent with experimental observations. The story of this constant is a story of how a number can reveal a new layer of reality. It reminds us that the universe may hide its deepest rules behind quantities so small they escape direct notice. Yet once uncovered, they illuminate patterns across phenomena that once seemed unrelated. Planck's constant transformed from a fitting parameter into a symbol of a new era, marking the threshold where classical intuition gives way to quantum truth. When the idea of quantized energy first entered physics, it did not merely solve a narrow technical issue about thermal radiation. It quietly altered the conceptual framework through which matter and light were understood. For centuries, light had been treated primarily as a wave, spreading smoothly through space, capable of interference and diffraction. Matter, on the other hand, was seen as composed of particles, solid bits of substance moving along definite paths. The introduction of energy quanta blurred these categories, forcing scientists to reconsider the nature of both. In the classical picture, an atom interacting with light was like a tiny antenna, continuously absorbing and emitting energy. The exchange could happen in arbitrarily small amounts, and radiation intensity could vary smoothly. Planck's proposal suggested that this exchange occurs only in fixed packets. This meant that atoms could not gain or lose energy gradually, but had to jump between distinct energy states. The smooth bridge between matter and radiation began to break into steps. This stepping behavior provided a new way to understand atomic stability. According to classical electrodynamics, an electron orbiting a nucleus should radiate energy continuously and spiral inward, leading to collapse. Yet atoms are stable and persistent. The concept of quantized energy allowed electrons to occupy certain allowed states without radiating, with radiation occurring only when an electron jumps between levels. This explained why atoms emit light at specific frequencies rather than a continuous range. The sharp lines seen in atomic spectra became signatures of quantized structure. Light itself also began to take on a new identity. If energy exchange between matter and radiation occurs in packets proportional to frequency, it suggests that radiation behaves as if composed of discrete units. Einstein extended this reasoning to explain the photoelectric effect, where light striking a metal ejects electrons. Classical wave theory predicted that energy should build up gradually, but experiments showed that electrons were emitted instantly when light above a certain frequency was used. This made sense if light delivered energy in individual quanta, each carrying a definite amount. The wave description alone could not account for this behavior. Thus, light acquired a dual character. In some experiments, it behaved as a wave, in others as a collection of particles. This duality was not a simple mixture, but a deep feature of nature. The quantization introduced by Planck made it impossible to cling to a purely continuous wave picture. Light could interfere like waves, but exchange energy like particles. The boundary between the two classical categories began to dissolve. Matter, too, was transformed. The idea that electrons and atoms possess discrete energy levels suggested that matter is governed by rules unlike those of macroscopic objects. Later developments showed that particles such as electrons also exhibit wave-like properties, with wavelengths determined by their momentum and Planck's constant. This symmetry between matter and radiation, both showing wave and particle aspects, was one of the most striking consequences of the quantum view. The new understanding explained why substances have distinct colors and chemical behaviors. The allowed energy levels in atoms and molecules determine which frequencies of light can be absorbed or emitted. Chemical bonds arise from quantized arrangements of electrons in atoms. The stability of solids, the structure of crystals, and the properties of materials all trace back to quantum rules governing electron states. What once seemed like complicated details of chemistry and materials science gained a unifying foundation. Another profound change concerned the way processes occur. Classical physics imagined smooth evolution, where systems pass through all intermediate states. Quantum theory introduced jumps. An electron does not gradually slide between energy levels. It transitions abruptly. These jumps are not visible in the macroscopic world because they happen at scales too small to observe directly, but they govern the microscopic interactions that underlie everything from light emission to electrical conduction. The relationship between observation and reality also shifted. In classical theory, measuring a system reveals properties it already possesses. In the quantum framework, the act of interaction plays a more active role, and outcomes are described in terms of probabilities. Planck's constant sets the scale of these effects. It signals that at small scales, certainty gives way to statistical description. Matter and light do not follow strictly determined paths, but exhibit a range of possible behaviors constrained by quantum rules. This transformation did not happen overnight. It unfolded over decades as new experiments and theories built on the initial insight. Yet the seed was the recognition that energy exchange is quantized. From that seed grew the understanding that the classical division between particles and waves was incomplete. Both matter and radiation participate in a unified quantum description where discreteness and continuity coexist in a subtle balance. The technological impact of this shift has been immense. Devices such as lasers rely on controlled transitions between quantized energy levels. Semiconductors depend on the quantum behavior of electrons in solids. Modern communication, computing, and medical imaging all draw on principles rooted in the quantum nature of matter and light. What began as an attempt to understand the glow of heated objects led to a redefinition of the building blocks of reality. The change in viewpoint also influenced philosophy. The world was no longer seen as entirely predictable from initial conditions. Instead, fundamental limits and probabilities entered the description. Matter and light, once thought distinct and well understood, revealed deeper layers of behavior. The universe turned out to be more intricate and surprising than the smooth, mechanical vision of classical physics had suggested. By introducing quantized energy, Planck set in motion a chain of ideas that reshaped science. The new view of matter and light did not discard classical physics, but placed it within a broader framework. Classical laws remain accurate approximations at large scales, while quantum laws govern the microscopic domain. The revolution lay in recognizing that the smoothness of everyday experience emerges from a deeper structure built from discrete interactions, a structure in which Planck's constant quietly measured the fundamental grain of nature. When the idea of quantized energy first appeared, it did not sweep through the scientific world with immediate acceptance. Instead, it entered quietly, almost cautiously, wrapped inside a formula designed to match experimental data. Many physicists saw it as a clever mathematical device, rather than a statement about how nature truly behaves. The intellectual climate at the time was shaped by deep trust in classical physics, and anything that challenged its smooth, continuous picture of reality was met with hesitation. Max Planck himself embodied this cautious spirit. He introduced discrete energy elements reluctantly, describing them as a formal assumption needed to derive the radiation law. He did not initially claim that energy itself was fundamentally granular. To him, it was a step taken out of necessity, not conviction. This personal caution reflected a broader mood among physicists, who were reluctant to abandon a framework that had proven so successful across so many domains. The first reactions to Planck's work were respectful but restrained. His formula accurately described Blackbody radiation, and this success could not be ignored. Yet many researchers treated the quantization as a technical detail, perhaps a feature of the interaction between matter and radiation rather than a universal principle. The deeper implications were not yet clear. Classical theory still dominated teaching, research, and intuition. The turning point began when Albert Einstein took Planck's idea seriously in a new context. In 1905, he used the concept of energy quanta to explain the photoelectric effect. His interpretation went further than Planck's, suggesting that light itself consists of discrete packets of energy. This claim was bold and controversial. Light had been firmly established as a wave phenomenon through decades of experiments. To suggest it also behaved like particles seemed like a step backward to older, discarded ideas. Many physicists resisted Einstein's interpretation, even though the explanation fit experimental results. Debate intensified as more evidence accumulated. Studies of atomic spectra showed patterns that classical physics could not explain. Niels Bohr proposed a model of the atom in which electrons occupy quantized orbits, with radiation emitted only when they jump between levels. This model successfully accounted for the spectral lines of hydrogen. Again, quantization proved useful, but it still seemed like a patch applied to specific problems rather than universal law. The scientific community gradually found itself in a situation where quantum ideas kept solving puzzles that classical theory could not. Yet the conceptual foundations were unclear. What exactly was quantized? Was it energy, motion, light, matter, or something deeper? Different researchers used different models, often inconsistent with one another. The early quantum theory was a patchwork of rules, each introduced to address a particular anomaly. Resistance was not simply stubbornness. The classical world view was elegant, continuous, and deterministic. It aligned with everyday experience and philosophical notions of causality. Quantum ideas, by contrast, introduced discontinuities and later probabilities, challenging deeply held beliefs about how nature should behave. Accepting them required more than technical adjustment. It demanded a shift in intuition. As the 1920s approached, the situation reached a critical point. Experimental evidence for quantum effects multiplied. The specific heats of solids, the structure of atoms, and the behavior of electrons in metals all pointed toward quantized energy levels. The old framework could not accommodate these findings without increasingly artificial modifications. A new theoretical structure was needed. This need led to the development of quantum mechanics, formulated by Werner Heisenberg, Erwin Schrödinger, and others. In this new theory, Planck's constant appeared at the core of the equations. Quantization was no longer an added rule, but built into the mathematical language. The theory predicted phenomena with remarkable accuracy and internal consistency. Gradually, the scientific community shifted from skepticism to acceptance. The transition was not smooth or unanimous. Leading figures such as Einstein remained uneasy about the probabilistic aspects of the new theory, even while recognizing its successes. Debates about interpretation became as important as calculations. Nevertheless, the practical power of quantum mechanics was undeniable. It explained chemical bonding, atomic structure, and a host of experimental results. Its predictions matched measurements with precision unmatched by classical approaches in the microscopic domain. Over time, the reaction of the scientific world transformed from cautious doubt to recognition that a fundamental change had occurred. Textbooks were rewritten, research programs shifted focus. Young physicists grew up learning quantum ideas as foundational rather than exotic. What began as a reluctant assumption became a cornerstone of modern science. This journey from resistance to acceptance highlights how science evolves. New ideas often enter quietly, supported by specific successes, but facing conceptual skepticism. As evidence accumulates and theoretical frameworks mature, the community adjusts, sometimes reluctantly, to a broader understanding. The response to Planck's quantum hypothesis reflects both the conservatism and adaptability of scientific thought. It shows how deeply held assumptions can be questioned, not by philosophical argument alone, but by the persistent voice of experimental fact. At the dawn of the 20th century, physics faced a subtle yet profound transformation. The initial steps of Max Planck, introducing the idea of energy quanta, had begun as a mathematical solution to a specific problem, the behavior of Blackbody radiation. But over time, this small step grew into the foundation for a revolution. The final keynote in understanding Planck's contribution is the way it laid the groundwork for modern quantum physics, reshaping how scientists conceive the universe at its most fundamental level. The quantum revolution began not with grand proclamations, but with careful observation and reasoning. Classical physics, for centuries, had provided an almost flawless description of macroscopic phenomena. It predicted planetary motion, mechanical systems, and electrical circuits with extraordinary precision. Yet, in the microscopic realm, subtle anomalies began to emerge. Planck's introduction of discrete energy elements was the first indication that at small scales, the world operates under different rules. The classical notion of continuity, so deeply ingrained in scientific thought, had to be reconsidered. Once the idea of quantized energy was accepted, its implications cascaded into multiple areas of physics. The understanding of atomic structure transformed. Previously, atoms were thought of as indivisible or, at best, as tiny planets with electrons orbiting the nucleus continuously. With the recognition that energy exchanges occur in discrete packets, scientists could explain why electrons occupy specific energy levels rather than spiraling endlessly into the nucleus. This understanding solved one of the central puzzles of atomic stability, providing the first clear path toward a coherent theory of matter at the microscopic level. Simultaneously, light, which had long been described solely as a wave, was seen in a new light literally and figuratively. The concept that radiation itself could behave as a collection of particles, or photons, challenged centuries of intuition. Experiments such as the photoelectric effect demonstrated that light's energy is delivered in fixed units, supporting the particle interpretation. Yet light continued to display interference and diffraction, characteristics of waves. The dual nature of matter and radiation became a central feature of quantum theory, revealing that classical categories were insufficient for describing fundamental phenomena. The reaction of the scientific community evolved gradually. Initially, Planck's hypothesis was regarded as a formal trick, a convenient mathematical device without physical reality. Over time, as experimental evidence mounted, from atomic spectra to electron behavior in metals, it became impossible to ignore. The quantization of energy was not a local phenomenon restricted to heat radiation. It appeared in diverse contexts, suggesting a universal principle at work. This universality hinted at the existence of underlying laws governing all microscopic interactions, paving the way for the development of a comprehensive quantum framework. By the 1920s, these ideas coalesced into full quantum mechanics. The work of Heisenberg, Schrödinger, Dirac, and others formalized the discrete and probabilistic nature of microscopic systems. Planck's constant, initially introduced as a proportionality factor, now became a fundamental component of the mathematical structure of quantum theory. Equations describing particle behavior, wave, functions, and uncertainty relations all incorporated this constant, revealing the scale at which classical intuitions break down and quantum rules dominate. This new framework provided unprecedented explanatory power. It accounted for the chemical properties of elements, the behavior of electrons in solids, the emission and absorption of light, and the stability of matter. Devices that underpin modern technology, from semiconductors to lasers, derive directly from principles that trace back to Planck's initial insight. The quantization of energy became not just a theoretical abstraction, but a practical foundation for engineering and industry, illustrating how fundamental science can ripple outward into applied knowledge. The shift in understanding also carried profound philosophical implications. Classical physics suggested a universe that could, in principle, be known completely and predicted with certainty. Quantum physics, emerging from Planck's insight, introduced intrinsic limits on knowledge. Measurements at microscopic scales are probabilistic. Outcomes can only be predicted statistically, and observer interaction influences observed phenomena. This reframing challenged long-standing assumptions about determinism and the nature of reality itself. The foundation laid by Planck's quantum hypothesis continues to influence contemporary science. Research into quantum computing, quantum cryptography, and quantum field theory all rests on the principle that energy and matter are fundamentally discrete at microscopic scales. Even in cosmology, the early universe and black hole physics are studied with tools developed from quantum theory, extending Planck's legacy beyond the laboratory to the very edges of space and time. In sum, the quantum revolution, which began with Planck's discrete energy elements, represents one of the most profound transformations in scientific thought. It replaced continuity with granularity, determinism with probability, and classical simplicity with a complex yet unified framework. By demonstrating that the world operates differently at small scales, Planck opened the door to a century of discoveries that reshaped technology, philosophy, and our understanding of the universe. What started as an attempt to explain a seemingly simple phenomenon, the glow of heated objects, became the foundation of a new paradigm, forever changing the way humanity conceives reality.